In this lesson, we will get a brief introduction to a collection of components that I usually use when designing analog circuits. We will see a few simple applications for each component, that way you can get an idea of the circuits you can build with them. The first component is the 555 timer. This is probably the most famous integrated circuit and it has many applications. The 555 consists of multiple subcircuits that, when combined, result on a versatile integrated circuit. In the diagram, you can see a functional model of the 555 that shows the different subcircuits. On the left, we have the voltage divider. This voltage divider is made using three similar resistors. With this configuration, we can get out of the power supply two voltages. The first one is 2/3 of the voltage and the second 1/3. In this specific case, the 555 is powered with 12 volts. Therefore, the first reference voltage will be 8 volts and the second will be 4 volts. Those voltages are connected to two comparators. The second terminal of each comparator is exposed as a pin of the IC, and we connect it anywhere we want. The comparators produce two signals that go into a special circuit called a latch. This latch is very easy to understand. One of the inputs is called reset, which is denoted by the letter R. When a pulse from the comparator is received, the output of the latch changes to a logic 0, which can be 0 volts. The second comparator is connected to the set input, which is denoted by the letter S. When a pulse is received, the latch changes to a logic 1, which can be, for example, 5 volts. The reset signal makes it output a logic 0, and the set signal makes it output a logic 1. This signal is connected to a switch. When the latch output is a logic 1, the switch is open, and when the output is a logic 0, the switch closes. The last subcircuit is an inverter and driver. The purpose of this circuit is to invert the output of the latch. If it is a logic 1, then it will return a logic 0 and vice versa. At the same time, it produces a signal capable of delivering more current. Let's see one application of this IC. Creating an oscillator with the 555 requires three external components, two resistors and one capacitor. We can see that the resistors are connected in series and provide energy to the capacitor, just like the RC circuit. The inputs of the 555 comparators measure the voltage of the capacitor. When the voltage of the capacitor reaches the 2/3 of the power supplies, or in this case 8 volts, the comparator will produce a reset signal that will make the latch go to logic 0, and this will close the switch. When the switch is closed, it creates a path for the capacitor to discharge, since one extreme of R2 is connected to ground. As we can see in the simulation, the capacitor will continue discharging until it reaches 4 volts. At that point, the comparator will produce the set signal of the latch, making it disconnect the switch. With the switch disconnected, the capacitor will start charging again and the process will repeat. The oscillation time is controlled by the values of the resistors and the capacitor. You can find the design formulas in the literature, or you can perform the analysis of the circuit. The next component I want to show you is a whole family of components. In the 555, we saw that it contains an analog switch capable of connecting and disconnect two points of the circuit, giving a control signal. Using multiple of these basic switches, it is possible to create a more complex configuration. For example, the ICs CD4051, 52, and 53 are different variations. The CD4051 can send a single signal to 8 different destinations. The CD4052 can take 2 signals and send each to 4 different destinations, while the CD4053 takes 3 signals and can send them to 2 destinations. The switches are controlled by one or multiple logic signals. We need to generate the appropriate signals depending on the type of switch. There exist many other analog switches with different configurations, but these are the ones that I use the most. The following component is called sample and hold. We can create this circuit using an analog switch, a capacitor, and an op-amp. The objective of the sample and hold is to take the value of an input signal and hold it for an indefinite amount of time. In the diagram, we can see how the components are connected. We have an input signal, which is the signal that we want to sample. Then we have a control signal. In this case, it's a small pulse. And every time the pulse is high, it closes an analog switch. When the switch is closed, the capacitor quickly charges to the input voltage through the resistor found on the switch, which is very small. When the short pulse ends, the switch is disconnected and the voltage remains in the capacitor. The capacitor is connected to a voltage follower, which creates a copy of the voltage that we can use without discharging the capacitor. In the simulation, we can see the results. In the bottom, we have the pulse that makes the switch close. On the top, we can see the input in blue and the output in orange. The output follows the input signal, but it has steps. This circuit is very useful to create signals in synthesizers. There exists an integrated circuit that makes things easier for us. It is the LF398. It provides the voltage follower and the analog switch on a single integrated circuit. We just need to add the capacitor. During this course, we did not cover how to build an analog multiplier. The main reason is that it requires multiple op-amps, and making a good design can be hard. Additionally, there exists an integrated circuit that performs this operation very well, the AD633. This integrated circuit has 5 inputs, X1, X2, Y1, Y2, and Z. The operation it performs is the following. It subtracts X1 minus X2, then it multiplies the value by Y1 minus Y2, divides the result by 10, and adds Z. This allows to multiply two voltages like 10 volts times 10 volts, which should be 100 volts. But as we learned before, op-amps cannot output more voltage than its power supply. For that reason, the result is divided by 10, then it is scaled to a voltage that is within the range of the output. When designing circuits around this IC, we have to consider that. The next integrated circuit is my favorite, the operational transconductance amplifier, or OTA for short. The most accessible of them is the LM13700. If you remember, regular op-amps have a fixed and very high gain, and they output a voltage. OTAs are a special kind of operational amplifier that have the following differences. First, they output a current instead of a voltage. Second, the gain can be controlled. Here we can see the symbol of the OTA. It looks like an op-amp, but at the output it has 2 circles and an extra terminal, which is the gain control pin. In the diagram, we can see the basic model of the OTA. This model works as the following equations. The output current of the OTA is the gain GM multiplied by the difference of the inverting and non-inverting voltages. The gain GM is variable and is defined by the formula 19.2 times the control current. We will see in the following slides a few examples on how to use OTAs. They are very useful components, but they do have a few quirks. First, the input voltage must be very low, less than 20 millivolts. If the voltages are larger, the input signal will be distorted. The control current is very low as well. It needs to be below 2 milliamperes. We have to consider these 2 requirements when making a design. The first example is a voltage control amplifier. In this case, we want an amplifier where we can modify the gain using an external voltage. This can be, for example, a volume control. In the diagram, we can see the circuit using an OTA. In the top, we can see how the control current is produced. We have the voltage V2 that flows through the resistor R5 and enters the OTA. The control pin has a voltage similar to the negative power supply. When the control signal is plus 12 volts, the voltage difference across the resistor R5 is 24 volts. That produces a current of around 1.2 milliamperes that is used as control. When the control voltage is minus 12, the current is 0 amperes. We can see the control current in the plot below. At the input of the OTA, we have the non-inverting terminal connected to a voltage divider formed by resistors R1 and R2. R1 is 10 kilo ohms and R2 is just 220 ohms. This will reduce a voltage of 1 volt to around 21 millivolts. This voltage is low enough to pass without much distortion through the OTA. The inverting terminal is connected to ground. The output current of the OTA is connected to a resistor, and according to Ohm's law, the voltage of the resistor is the current times the resistance. In this case, the resistor is 1 kilo ohm. That means that the output current is multiplied 1000 times and converted to voltage. In order to measure the voltage of the resistor and not consuming any of the output current, we connect a voltage follower to the resistor. In the simulation, we can see the input voltage in blue and the output voltage in orange. We can see how the amplitude changes depending on the control signal. If we take the same circuit and we change one component, the resistor at the output, and we place instead a capacitor, we get a variable gain integrator. If you remember one of the initial lessons, we learned that we can charge a capacitor using a current source. In this case, the output current goes into the capacitor, and according to the differential equation of the capacitor, we have an integrator. In the simulation, I have added as input a constant signal of 1 volt. The control current is the same as in the previous example, and it can be seen in the bottom plot. In the top plot, we can see the output in orange. We can see that the rate changes. When the control current is low, close to zero, the integrator does not grow. If you remember the analog filter lesson, by adding feedback to an integrator, we can create a simple low-pass filter. This diagram shows the same integrator, but adds the resistor R4 as feedback through the inverting input. In the simulation, we can see that the input signal is a square wave. As the control current increases, the cutoff frequency of the filter increases, and we can see in the output, shown in orange, the filtered signal. Having a variable gain integrator allows us to make many interesting circuits. In the final lesson of this course, we will use them again. There are a few small semiconductor companies that fabricate special integrated circuits for musical applications. I have used ICs by Alpha, Sound Semiconductor, and Cortes Electromusic. Over the years, these ICs have been used in multiple analog synthesizers because they perform many common operations in a single IC. We can find OTAs, oscillators, filters, and voltage-controlled amplifiers. These circuits have the following advantages. They have exponential control. In musical applications, it's more common to use octaves, just like the keys of a piano. For example, in a piano, if we play a middle A note, it will have a frequency of 440 Hz. If we go one octave above, the frequency will be 880 Hz. Every octave, the frequency doubles. In order to produce this behavior, we need exponential control, and these circuits provide it. The second big advantage is that they usually add temperature compensation circuits. The semiconductors change their characteristics as they heat up. In the case of oscillators, this can result on the oscillator changing the tuning, and therefore making it sound bad in combination with other instruments. Temperature compensation is needed in order to minimize the change in tuning as the temperature changes. The last component I want to talk about is the vactrol. A vactrol is a component made by a photoresistor and a light source like an LED. A photoresistor is a special kind of resistor that changes value depending on the amount of light it receives. When it has no light, the resistance is very high, around 10 megaohms. As the light increases, the resistance lowers until it reaches a value of a few ohms. In order to control the resistance, we use a light-emitting diode or LED, and by putting them one in front of the other and wrapped by an enclosure that avoids exposition to external light, we can control the resistance by changing the current of the LED. In the picture you can see a vactrol I made. Vactrols have a few quirks. They are non-linear, so it's not possible to precisely control their behavior. They also have large variability. The ones I have built, when controlling them with the same voltage, result in different values of resistance. Another issue is that they cannot follow very fast the control signal. For example, if you quickly change the control voltage, it will take some time to change the resistance. There exist commercial vactrols as well, and those tend to be more reliable and have lower variability than the homemade versions. One simple application of the vactrol is to replace potentiometers. That way we can change the behavior of a circuit using a voltage. In the diagram you can see a variable RC filter using a vactrol. On the top, we have the control voltage that changes the resistance value, therefore changing the cutoff of the filter. As a summary for this lesson, we discovered a collection of components that I usually use when building synthesizer circuits. We had a quick overview of the 555 timer, which has entire books written about their applications. We learned a few configurations available of analog switches that we can use to control the flow of signals. we learn my favorite IC, the OTA, which has many applications in synthesizer circuits. Last, we learn vactrols, which are components that can be used in place of potentiometers in order to control them with a voltage.